Resonance, we talked about using your arrows to draw resonance structures. Lone pair, we're looking to delocalize the charge. Some of you gave resonance structures in which the charge was not delocalized. How do we stabilize an anion? Move electrons away from it. Electrons here, electrons out, in and out. This puts lone pair here. A number of you are just not seemingly able to do that right there. Electrons in, electrons out. We can keep going. Resonance structure here. This would be your major resonance structure, anion on oxygen. 6 pi electrons, if you understand your p orbitals. 1, 2, 3, 4 electrons, and then a lone pair from the nitrogens in a p orbital. We looked at that type of thing back during like week 2 and 3. Amine, this guy here, this lone pair is not conjugated. There's no resonance with this lone pair, and so it's going to be the most electron rich. All these lone pairs are delocalized into the ring by resonance. So they're less electron rich. This one over here, you can look at it. If you look at both allylic cations, you'll see that this allylic cation is going to be the better one. Resonance, put cation there. We're doing the heat, so we're looking for the most stable product. So adding chlorine here to give this product. This is the most stable product. Any questions about any of these? Joule-Zolder, pretty straightforward. 4 plus 2 is 6, not 5 or 4 or 3 or anything else. Many of you forgot your alkene here, which comes from this arrow right here, putting alkene there. These would be trans. Variety of interesting answers given here. Acylium ion. Only cations observed in mass spec, not anions. Very funny little things like that, guys. If you don't understand that only cations are observed in mass spec, then I don't know how you can go any further than that. Okay, this is posted upstairs. Any questions on the quiz? I think there were 2 or 3 10s, a couple of 9s, etc. Good job on that. Okay, let's pick back up with substitution. Williamson ether synthesis, sometimes abbreviated WES. So we looked at that over here. Before you can react, you're starting with an alcohol or a phenol or carboxylic acid. Although when you use a carboxylic acid, you're not making an ether. There you're making an ester. But typically these have to be deprotonated to turn them into the better nucleophile, right? Once you make the better nucleophile, then you can come in with a carbon with a leaving group and you can make the O carbon bond and you can get ultimately an ether. And so let's look at this one over here. In this example, we're going to make a ring. This isn't ether, it's a cyclic ether. We take this compound treated with sodium, we can get this product called sodium bromide. What does sodium do to this compound? The only thing you know is that sodium is going to do what to the alcohol? It's going to basically form the alkoxide anion, right? Boom, boom, boom. Boom, boom. Make that plus what? Plus hydrogen gas, right? Okay, what can this guy do? Well, to make a ring, we want to have an internal reaction, an intramolecular reaction. This guy then comes over here and does an internal SN2. What does this give? It gives a 1, 2, 3, 4, 5-membered ring. It gives that, plus ultimately sodium bromide. Of course, you know this is ionic, right? This is sodium ions and Br minus ions. The Br minus is formed right here. The sodium was formed when we made the alkoxide. That's the fate of this original sodium metal. So that's a hopefully pretty straightforward example of an intramolecular Williamson ether synthesis. Yep, pretty straightforward. Questions about that one? Making rings here? So such as possible. Going backwards. Synthesis. We'll do much more synthesis in organic too. How would you make this compound? We did maybe a little bit with alkenes. Well, the main functional group here is an ether. Because typically you do reactions around functional groups. It's very hard to make this bond here. You just don't have any reactivity much here. We have an ether. What's the best way to make an ether? Yeah, Williamson ether synthesis. So good of a way it gets its own name. Okay, what does a Williamson ether synthesis involve? What are the reactants? An O minus, an alkoxide or phenoxide. O minus, right? What was the other component?
Does it have to be a halide?
Sodium what? Well, not if, I assume we already have the alkoxide. The alkoxide and what? The alkoxide and somebody tell me. What are the components of Williamson ether synthesis?
Hydroxide?
Alkoxide and hydroxide?
Sorry, yep.
Alpha halide?
Ah. I mean, right here. We have an alkoxide or phenoxide, and you need a carbon with a leaving group because this reacts with that. Okay, so break this into your two components. Your alkoxide, the O minus, and the carbon with the leaving group. That is, which bond do you want to make? Do we want to make this bond here? Carbon reacting with carbon? I don't know how you would do that, really, I don't. How about this bond? Oxygen reacting with carbon? Would you do that? Break it into two components. Break it into the O minus plus what? Okay, very common. We're going backwards. When we go backwards, we use sort of a double line arrow like this. So retrosynthesis arrow, retro, going backwards.
Does it matter any L halide? Any alcohol?
Let's get there. How about that plus propane? Can we go back to those two starting materials? That is, if we had these two, would they react and come this way and make this? How would they react? Would these two react to give this?
Because you have to have a charge.
Why would they not react to give that?
Charge.
Propane would react with it.
What?
Propane would be inert in that reaction
Why is it inert?
because there's no charge on it. It doesn't want to react with oxygen.
So it has to have a charge on it to react?
Not exactly, that's at the leaving group.
Ah, okay. Let's put a leaving group on one of these carbons. How about that there? Can you envision a reaction now? Yes, now these electrons can come in here and kick off the leaving group. What does that give? What does that mechanism give? It gives this. Yes, we have to have a leaving group. Otherwise, if it was just propane, we'd have to lose an H. I don't know how you would lose an H. So, a retrosynthesis arrow. Could we go back and propose another route? Could we go back another way? What's another way to make this product? Could we make another bond instead of the one we made there? This is bond A we just made. Could we make another bond?
Did you do a ring contraction or ring synthesis?
To make the carbon reacting with carbon to make a ring?
Yeah.
Two carbons reacting with each other is very difficult again. I mean, that's 600, we'd like to do a Diels-Alder, but Diels-Alder is going to give a double bond, and we got to get rid of it. Provided Williamson ether synthesis sort of gave you some. Is there another Williamson ether synthesis we could do? What about this O carbon bond over here, B? What about reacting? This alkoxide with cyclohexane. Would that give that? If these reacted, would that give that? Or do we need a leaving group here? How about an OTOS? Is that a good leaving group? Leaving group. Would these two react to give that? That is, we went forward instead of backward. Yes, this is two different Williamson ether syntheses. Leaving group doesn't matter. I could have put tosylate over there. I could have put iodide over here, the LG. So this is two different Williamson ethers. Question though, which one's better? Which one would you think would give the highest yield and you would more likely propose? Which route looks better? Don't worry about leaving groups because we could have put any leaving group here. Anything else to distinguish them? Yes, here the nucleophile is attacking a primary carbon, primary halide. Leaving groups on a primary carbon. Here the leaving groups on a secondary. Which would be better for this SN2 reaction? Yeah, having your leaving group on a primary. We looked at that a couple pages ago, right? Route A would be better here because leaving group's on primary carbon. Here it's on secondary. What if one of our potential routes, the leaving group had to be on tertiary? You wouldn't even do that because you can't do that reaction. I mean, you can at least do one on secondary. It's going to be slower than primary. What did we say about tertiary? I think we gave some exclamation points.
Impossible.
Never SN2 with leaving group on tertiary, right? So, well, how would you make the alkoxide? If you were asked to start with neutral molecules, how do you make this? We could go backwards, but I'm just going, right? We would just have the alcohol, right? Right? We convert that to this how? So what?
Strong base.
What's your strong base of choice here?
Sodium hydride.
Sodium what?
Hydride.
Sodium hydride? Sodium hydroxide. Does sodium hydroxide make alkoxides? Look back at the other page, it had a big X through it. The one with the big X? That was using sodium hydroxide. What does the big X mean? Doesn't work, right? So what base works with alcohols?
Sodium metal.
Not really a base, it's sodium metal, but it acts essentially as a base. Yeah, sodium metal. Sodium hydroxide doesn't work. We showed that on the previous page. Big X. You said sodium hydride. I didn't mention sodium hydride. Where did you pick that up?
Supplemental class.
Okay, sodium hydride. In practice, I don't think I would recommend it here. Textbook is probably okay. Okay. Williamson ether. And there's probably some Williamson ether questions in your workbook, etc. I think including probably one about morphine or codeine or something. I think there's an entire page about that. Okay, so we just alkylated oxygen. What about sulfur? Right below oxygen. Any of the reactions we just did, you can do with sulfur analogs, sulfur compounds. Very analogous. What I would say about sulfur is that sulfur is perhaps your body's most reactive nucleophile. Your body uses sulfur as a nucleophile a good bit. It also uses sulfur as leaving group a good bit. We showed an example before with SAM when we converted norepinephrine to epinephrine. Your body uses sulfur. SH groups are in lots of amino acids, or lots of proteins because they're in amino acid. Which amino acid has an SH group? Y'all learn amino acids in biology or something? Cysteine?
Yeah.
Yeah.
Boom. All that from test one material. But yeah. The only thing I've learned in sulfur. It's like the only thing I learned.
A small peptide that's in your body is called glutathione. The tripeptide, it serves as your body's sacrificial nucleophile. Okay? It has this reactive SH group. Now it's neutral, although in some areas of the body with higher pH, this may exist as an anion. And when it's an anion, it's a pretty darn good nucleophile. Sulfur, in the neutral state, is a decent nucleophile, although based on our classification, would we call this strong or weak? Is it an anion? No. Is it sp3 nitrogen? No. Then it would be weak. But what I'm telling you is, it's got a little bit of strength to it. Get it in an anion form, it's really good nucleophile. Okay? But this tends to be the reactive nucleophilic site. And you get something in your body like methyl iodide. Very reactive electrophile. That is, electrons like to come in here and kick it off. Okay, your proteins come in here and kick off the leaving group. All right, your DNA has amino groups come in here and kick off the leaving group. And you've alkylated your DNA and your proteins. Bad, bad, bad. Instead, this guy comes along and kicks it off. That's okay. This is the role of this guy. It's there to save the day, to serve as a sacrificial nucleophile. So it reacts instead of your DNA, instead of your proteins. Then, once it becomes alkylated and you put a methyl on this sulfur, then it gets washed out of the body because these are typically ionic, and it's very water soluble and it can get washed out of the body. So that's glutathione. Sometimes drugs behave on this principle. Mucomist. Anybody know mucomist? Nurses or anything? No? If you overdose on Tylenol, they'll give you mucomist. Because Tylenol forms a reactive electrophile. All right, I'm not going to show it, but it's something that nucleophiles will attack. And the proteins in your liver attack that and it ruins your liver. Instead, we give you this, and this goes and attacks the Tylenol metabolite instead of your liver doing it. Because it's a good nucleophile. So that's a little bit of sulfur. What about nitrogen? Nitrogen. Well, a neutral sp3 nitrogen is a good nucleophile, right? Okay. The simplest nitrogen would be ammonia, NH3. It can do an SN2 because it's considered a strong nucleophile. This would be ultimately we're going to call this a direct alkylation. These electrons come in here and kick off the leaving group. What does this give? It would give this here. The NH3 is now bonded to the carbon. And the Br minus was produced. That is, the neutral nucleophile became positive once it made another bond. Where in the past we've been starting with anions and they became neutral when they made another bond. So this became positive. Now to go neutral you need to lose an H. And we can go to new neutral. And now we say the nitrogen has been alkylated because there's now an alkyl group on the nitrogen. But let's look at this. Will Br take one of these H's to give this plus HBr? Will that take place?
Very little.
Well, that's an acid-base reaction. How do we judge acid-base reactions?
The strength of the acid.
pKa of each side, right? pKa of this is about 10. It's an amine protonated. pK of HBr is about what? About -5. It's a strong acid. Which side's favored, 10 or -5? Which side?
The left side.
This side's favored. So is Br going to take an H and go that way? No. This side's favored. It's going to stay like this. So the anion is not going to take the H. To go neutral, you have to bring in some other base. For example, hydroxide, a stronger base. It will take the H, okay? Or potassium carbonate. Now, a lot of times these will be included in the reaction here, or you can add it after the reaction. The Br minus is not strong enough to take it. We see from that equilibrium. Now, let's go to the very first. I don't have it in this handout. I have to find my other original. Do you have your original, the one you printed? I should have included it. I never find it. Anybody have the first page?
I do.
Can I show it? No, the original.
Yes.
You want me to change
This
it?
is
No, when you printed it? Yes. Okay. We showed this before, but now let's go back and look again. 31 is going to 32. Here's the reaction error. So they didn't put the here. It's coming this way. What's going on? They're making this bond right here. Nitrogen binding to carbon. From this amine, okay, we have an amine. It's not ammonia. It's a secondary amine. But this nitrogen is reacting here and kicking off the leaving group. Now, this is a mesylate. As I said, mesylates are used, but for us, more common is tosylate, right? Mesylate's similar. Okay? That's what they're doing here. It's a good old SN2 reaction. Strong nucleophile, right? Why does the oxygen not react and kick off the leaving group? It's got a lone pair. Is this a strong nucleophile? Is it an anion? Is it an sp3 nitrogen? Not strong. And we said to do an SN2, you got to have strong. So we wouldn't expect that to do it. But that is strong. Kicks it off. It's got an H here, though. Where did the H go? It doesn't magically disappear. When it kicks it off, you get that. Something has to take the H to go neutral. Well, why do you think they include potassium carbonate? Carbonate there is a base that would take the H, leave the lone pair behind, and they show the neutral product. So they included the base in the reaction. That's just solvent. That's acetonitrile. So just the solvent. They refluxed it 72 hours. So it wasn't just 15 minutes. It was, what's that, 3 days? That's kind of a long time for an industrial synthesis. I'm quite a little surprised. Why was it so slow? Why wasn't it super fast and done in 15 minutes? Can you give any argument for why it might be slow? Would it be faster if we had used ammonia instead of this secondary amine? The secondary amine has these wings on it, right? Right? What? Right? There's the carbon with the leaving group. Here's ammonia. Boom. Backside attack. Right? I did this before. Let's put wings on. Uh-oh. I'm now knocking into everything. Uh-oh. Uh-oh. Oh, now it slips through. One gets through every 10 minutes as opposed to every split second. That was much slower, right? It's a secondary amine. What if it was a tertiary amine? What do we say about tertiary amines? We said those are typically non-nucleophilic and they're actually used as bases, right? So it's a pretty hindered amine. That's why it's probably slow. This carbon's primary, so there's not any hindrance here. Steric hindrance there. I think it's probably because it's a secondary amine. Right? Important thing though, guys, anything we just discussed there, was anything not covered before? You guys got to work on taking information and putting it into context and seeing why everything is important. I think you guys just seem to read and let it just slip by and gloss over it. Where was that at? But there's a problem with this direct reaction. The problem wasn't apparent in that first page example. The problem, though, is polyalkylation. That is, if you're trying to just put one group on, 0 alkyl groups on the nitrogen, now we have 1 alkyl group on the nitrogen. You try to do this directly, the problem is you're going to end up with 2 alkyl groups. And you may even end up with 3, even if you don't want 2 or 3. So how does it keep alkylating? First off, is this a good nucleophile? That is, if we have some of this still around, is this going to react with this? To do an SN2, you've got to have a lone pair to do backside attack. This has no lone pair. It's not a nucleophile. Not only is it not an anion or neutral, it's actually positive. So it's not going to be attracted to a partial positive carbon. Okay? But this is a good nucleophile. It can react again, but you don't get that unless you add base. Even if you don't add base, you can get this chemistry going on. Ammonia can take the H from this, because ammonia is there. Okay? Ammonia can take the H. That gives this. Ammonia acted as a base and gave that just like that. And we maybe make ammonium bromide. Now this can come in here and alkylate again. And it alkylates. You're going to get a positive nitrogen, but then something can take that H to go neutral. And so this can alkylate a second time. And then this guy can actually alkylate a third time. And this is often a problem when you try to do a direct alkylation of an amine. It's further alkylation. Any questions about this? I could talk about this for 10 more minutes, but I only want to talk about what you have questions about. Because I don't want to say stuff that you understand. I'd like to hear what you don't understand. Talk about that. So, any questions about this mechanism, this equilibrium? Okay. Alternative approaches to direct alkylation. Let's make the same compound again, but this time in much better yield, without polyalkylation. There are a variety of ways to do indirect alkylation. I don't think it says indirect up there, but it's an alternative to direct. It's called indirect. Here's one way to do it. Sodium azide. We haven't seen that before, although you did a Lewis structure back in week 1, week 2. Azide, what's the charge of N3? The net charge of N3? Negative, right? Yes. Remember your Lewis structure? Okay, it's actually all three nitrogens are charged, but it's net minus. One of the terminal nitrogens comes in and does an SN2, and then the N3 is now bonded to the carbon. Okay, this is condensed down. There's a structure there. N3 bonded to the carbon by SN2. Good yield here. This is not going to alkylate again. Even though you got an anion here, it's not going to alkylate again because it's really net neutral. You might argue that it could, but it doesn't. The N3, this product can then be reduced with hydrogen and palladium or platinum or something, and you can get the primary amine, and you don't have any risk of polyalkylation. The fate of the other two nitrogens, I'm actually not sure. It may form nitrogen gas, or it may be some type of reduced nitrogen. So it's an indirect method to make alkylated amines. We're also introducing azide as a potential nucleophile. We've got anion here. In organic 2, you'll see a couple of different ways to make amines, alkylated amines, by indirect methods, particularly when you get to carbonyl chemistry. One last thing about nitrogen nucleophiles. Quaternary ammonium salts or amine salts. Now, hopefully there's a question about this, and let's see if any questions come up. Look at this reaction note. You take this amine, this lone pair, come in and do your SN2. We're going to make this bond here. Now this does not have a hydrogen to lose to go neutral. Even if it did, the Br minus would not take it. But it doesn't. This type of product is a quaternary nitrogen. Because the nitrogen is bonded to 4. And when it's bonded to 4, it's going to have a positive charge. This is called short a quat. So quaternary ammonium salt. It's an ionic product. And this can be an end product. Again, as a salt. Now quats are seen some in biology. Have some useful properties, useful molecules. You guys know choline or acetylcholine? Okay, choline is, you have a quaternary ammonium salt. It's a quat. And then acetylcholine, that's when this is just an acetyl group that's been put on the oxygen. All right, and that would be organic 2 chemistry, carbonyl chemistry. But you always have this quat. A lot of hand antibacterials. You guys maybe have some in your purse. Yeah, you got, no? A lot of times those are just alcohol, but sometimes they'll have something in them like didecyl dimethyl ammonium chloride. What is this? What is decyl? 10 carbons? 2 10-carbon chains. Dimethyl, 2 methyls. Ammonium, because it's a positive ammonium, and then the anion. Okay. This is a common topical antibacterial. Apparently the ions disrupt the, I don't know, do bacteria have cell walls?
Yes, but they're made of different.
Okay. It can kill the bacteria probably by disrupting cell walls or something, membranes, some of that stuff. You ever been over to the Y over on Walton Way Extension?
Mm-hmm.
They got hanging on the walls antibacterial stuff. Next time you're over there, look at it. It's got a label on it. It says didecyl dimethyl ammonium chloride. That's why I drew that structure. I mean, there's several of them. That's the one over at the Y. Okay. Any questions about this chemistry, though? Yes, great question. Tertiary amine. Why is it doing an SN2? Right? Everybody was wondering that? How's a tertiary amine? I thought you said no. Yeah, well, this is an exception. All right? Because the no is a great starting point. Your first thought should be no, 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 no. But quats can be made. It's actually a tertiary amine reacting as a nucleophile, right? I want you to recognize that. Now, this probably requires a good amount of heat, maybe a long time, but okay. So every reaction you need to dissect and what's going on here. My nucleophile. Let me look at it for a little bit. My carbon with the leaving group. Let me look at it. What are the conditions? Any stereochemistry? Well, not here. You ever seen a book in the library? Y'all know where the library is? There's a book called World Records in Chemistry. Great book. World record for the most bitter compound. Okay, now you typically don't want to be tasting compounds, but sometimes people do. I don't recommend it. This apparently is the world's most bitter compound. Wow, that's a lot of carbons. What is it? It's a salt. There's a plus, there's a minus. Ion pair. Both ions are organic. I mean, one of your smallest salts would be sodium chloride. There's an ion pair. Well, this is also an ion pair. But the cation is a quat. Right? Quaternary ammonium. And this is called I've never heard it pronounced, denatonium benzoate. Yeah, that's benzoate. It's added to like antifreeze to keep your cats and dogs from drinking the antifreeze. Because they start drinking it, antifreeze tastes good. Put that in there and they're like, I don't want that. But it can be used for some good purposes. Yeah? World's most bitter compound. Okay, we looked at oxygen, nucleophile, sulfur, nucleophile, and nitrogen. What about carbon? Can carbon be a nucleophile? Can a neutral carbon be a nucleophile?
No.
Neutral carbon don't have a lone pair. Unless it's a carbene or something. But a standard neutral carbon, no. Right here. Is this a nucleophile? Pi bonds typically don't do substitution chemistry. They act as nucleophiles with protons and electrophilic reagents like BH3 and stuff and bromine. They typically don't do SN2, SN1 with. Typically you need a lone pair to do substitution chemistry. Ain't no lone pair. Can we make a carbon with a lone pair? Yes. This is an alkyne. This H has some acidity. We can deprotonate it. Remember, this is the last thing we did for test 2 material with the miner's helmet. What base did we use to deprotonate a terminal alkyne? I showed you 2 bases. And actually, sodium hydride is often used here as well. 2 I showed you were... What 2 did I show you? One of them was on the bottom question of page 1 of test 2. It was a base that was used and then the product was treated with D2O.
Let me get
I don't have the handout, but I have the test. Yeah, NBO lithium, right? That's test 2, bottom of page 1. Right? What other base did we use? Yeah, the other base we used was NaNH2, right? Plus minus. These electrons take the H, these stay behind, and we can get the benzene ring phenyl with we can generate the acetylide anion. I would look back at this in the alkyne handout. It was the last page of the alkyne handout. And actually there was a note there. I said that in test 3 we'll use these acetylide anions for substitution reactions. Well, now we can do that. Now we have a good nucleophile. Lone pair, and it's an anion. Now we can come in with some type of carbon with a leaving group. Let's come in here with another phenyl group. I'll put a deuterium there. How about that? What's the product of this reaction?
I don't know what the name of it is, but would it be 2 phenyl groups?
These electrons going to kick off the chlorine.
You didn't want to take the deuterium?
Is that right? Which bond did we just make? Right there? That was the carbanion. Now bonded to the carbon that had the leaving group on it. Carbon with the leaving group also had the D in the phenyl. Carbon with the leaving group also had the D in the phenyl. We made that bond right there. This stereochemistry here is Cl phenyl, that's R. This over here is drawn as, oh, actually, I just realized that I probably drew it wrong. This is what, group. Yeah, that should be like this. This here is, phenyl is this. Oh, that's actually tough.
What has higher priority? Are they the same DNA, deuterium and hydrogen?
That's actually tough. I mean, it's going to take some, this is higher priority, I believe, because this carbon has 3 bonds to carbon, that carbon has 3 bonds to carbon. You go to the next carbon, this carbon has 3 bonds to carbon, and this one has a bond to an H. So that's 1, 2, 3. Right, that's S. Okay. Inversion, right? SO2 comes with inversion. Just like your Big Mac comes with fries. No, it don't? Okay. In lab this week, we'll probably be looking at UV vis.